All right. Okay, time to start. Welcome again to our seminar for February, the Fueling of Tomorrow of ASAFA, the Asia SAF Association. This is Fabrice speaking. Happy to have you on board. Today, we will talk about a topic about eSAF, all right? So a topic for very promising for the SAF production. I'm talking to you directly from Abu Dhabi this week. And in fact, eSAF, as you can imagine, in the Middle East is a big topic, but it's not specifically in the Middle East. Also, we have Asian leaders on that topic, and we'll be delighted to introduce to you Yasushi Hashimoto and Dr. Lu Wei Cheng. We are going to speak today from IHI Corporation and from A-Star. Hello to the two of you. Yasu, Lu Wei, you're with us. Hello. Good afternoon to you.
Good afternoon, everyone.
Thank you very much. So before passing the mic to you, I just have a few slides about ASAFA quickly, so to make sure that we all align and to give you a bit of updates of what we have been doing recently. So first of all, I want to share with you and with the people joining to us about the mission of ASAFA, right? So we are an independent non-profit association. And I think all the words here are important because we're independent, because we're not country specific. We're looking at the region, at Asia, and the whole Asia. And also we're independent because we are gathering the whole ecosystem of players from the SAF industry. So we're not focusing only on one single industry in this. Our missions, of course, accelerating aviation decarbonization. Okay, fair enough. It's true for everybody. But how do we want to do that? We want to dig further in terms of advancing policy and market integration to work on policy frameworks at the regional level so that we have a common playground and common battlefield for everybody on SAF in the region. We want to ensure diverse and sustainable supply chain dedicated to Asia. We want to enhance technical expertise, building capacity and technical proficiency from the public and the private sectors. And last but not least, we want to enable investment as well by mobilizing financial investment to support both R&D, but also the scaling up of SAF infrastructures. So today we have members and partners with us. So we have Korean Air, Total Energy, 1.5, A-Star, Bureau Veritas, DHL, Airbus, EU ASEAN Business Council, General Index, Sustainable Aviation Fuel, Marquis Energy, Quantum Commodity Intelligence, GU, Sky Energy, Key, SAF1, and LanzaJet. And we are working to have with future members to join us as soon. So stay tuned. Okay, this is our leadership team. So I'm on the left hand side, but we have also Wei Ling, Dietmar, and Gabriel as part of the leadership team. So we've been quite active again recently. Gabriel was in Tokyo in January, attending the ISCC Plus and SAF conference. He was a speaker there. I think with very positive exchanges with people there. I am currently, I mentioned to you, in Abu Dhabi, all right, for the SAF MENA Congress. And it's organized in parallel with the ICAO GISS. So we have also a lot of governments joining us for that event. Gabriel will be speaking next week in Singapore at the Marina Basin about commodity trading markets and on SAF, of course. He will also be speaking in Singapore to the Fuel Summit as well, the following week, to the Low Carbon Fuel Summit. And I will be speaking in Sarawak the week after for SAF at the EIC Connect Energy Borneo Summit. For the event today, please, we are important. The feedback is important, so we know where we stand. And of course, our purpose is always to improve the content, but also the format of the webinar. So please give us our feedback with the survey that is going to appear on the browser when the seminar ends. Thank you very much. And without further ado, I will leave the floor to our distinguished panelists today, our distinguished guests. So first to speak, Yasushi Hashimoto. He's the R&D Manager for IHI Corporation. So for those of you who don't know IHI, it's a Japanese engineering corporation that produces and offers heavy machineries, products, infrastructures, and services such as aircraft engines, rocket, gas turbine, plant engineering, and suspension bridges. Yasu has been assigned to the current position in the Commercial Jet Engine Technology Division to manage both the production and the utilization aspects of SAF, Sustainable Aviation Fuel. He also acts as the advisor to the Public-Private Council for SAF deployment in Japan, which is run by the Japanese government, and is based from his past experience of leading IHI microalgae derived SAF projects, which the fuel is now approved in International Jet Fuel Standard ASTM. Yasu has been one of the early SAF evangelists in Japan, so we're really glad to have you on board, Yasu, and engage in SAF activities in form of lecturers, article authors, and advisor roles. So please, Yasu, the floor is yours.
Thank you, Fabrice. So let me start out with sharing the screen. Please let me know when you let me do this full screen. And yep. Pointer. Do you see the pointer?
Perfect.
Good. Thank you. Thank you again, Fabrice. Let me turn off the video to, I'm sorry, to get my load off a little bit. Okay, good. So thank you again. Hello, ladies and gentlemen. My name is Yasushi Hashimoto. My full name is Yasushi, but you can just call me Yasu in short. I'm the R&D Manager on Sustainable Aviation Fuels in IHI Corporation. Like Fabrice mentioned, I'm working both on the SAF user and SAF producer side. Engineer by degree, and my main work is business development of IHI Sustainable Aviation Fuel activities. I also serve as a technology advisor in Public-Private Council for the SAF deployment in Japan, run by the Japanese government agencies such as Ministry of Energy, Trade and Industry, and Ministry of Land, Infrastructure and Transport. I am very happy and honored to be given this opportunity to present in front of diverse audience. I would truly like to thank ASAFA founding members Fabrice, Wylene, Gabriel, Dietmar for this wonderful opportunity. And I would also like to thank A-Star for providing a privilege to co-present in this webinar. Lastly, before going on to the main topic, congratulations ASAFA for such a fast-growing movement. I'm going to touch on this later on, but we do need unity and coalition effort for decarbonization of aviation sector. And, we are, some of you might be competitors in some way, but, more than that, I think we're all friends, colleagues, allies to tackle this global difficulty. So thank you again for ASAFA. Okay, so let's go to the, and set that, and only to find out, okay, good. So today I would like to introduce IHI's activity on SAF. We are a technology challenger of power to liquid. One disclaimer here is that the technology itself is not on market yet. And this is sort of a teaser to what to come in the future. And in that sense, I would like to use this opportunity with this vast audience that all involved in sustainable aviation fuel, which is really a fabulous thing. It's now 59 members, participants now, again counting, and to have some lively discussion on what our technology could make of in Asia. And I sincerely hope that my presentation could spark some interest and stir some discussion in Asian, sustainable aviation fuel outlook. Again, since I'm coming from this business development field where, subtleties and sincerities and thoughtfulness is seldom, or let's say, well, often maybe abbreviated, the technology aspect of our catalysis will be covered in the presentation that followed by Dr. Wei Chan. So that's more a technological oriented presentation. So yeah, IHI has worked extensively with A-Star, Easy Squared throughout the years, and Dr. Chen is a lot more capable and appropriate to explain our technology. So I'll be more on the general side of a presentation. That's one disclaimer here, okay? Okay, so a little bit of, let's dive into the content and a little bit of our advertisement of our company. So again, as Fabrice mentioned, IHI Corporation is a heavy machinery manufacturer from Japan. Our headquarters office is located in central Tokyo. And we have four main business pillars. All of them, with few exceptions, are large structural machineries, such as the power generation plants. That's pictured here. Power generation plants, bridges, parking systems, and jet engines and rockets. So my work on the SAF user side comes on jet engines department. More than 160 years of history, but we are not state-owned company. But a lot of our revenue comes from the national project. And yes, future carbon neutrality of aviation is a mission for Japan and mission for the IHI as well. So like many of the manufacturing sectors, especially with a sizable portion of revenue coming from jet engine production, we too pursue a mission to decarbonize our company activity. And heavy machinery manufacturing is vast technology portfolio. So in that sense, we now envisage that our technology could contribute not only to our own company activity, but to the decarbonization of various industrial sectors, especially aviation. And sustainable aviation fuel is just that. We are just showing just part of the portfolio that we are in, or business areas that we are involved in for this slide. So many of you might know that the IHI had invested in SAF for quite a long time now, that we worked on sustainable aviation fuel even before the terminology SAF was coined. In the days when it was called biojet fuel or alternative jet fuel, like AJF, we started touching on sustainable aviation fuel. It started 14 years ago in 2011, and it was a bio-SAF. I would not go in detail today's presentation on power to liquid, but just to show you the background of where the IHI's sustainable aviation fuel know-how is coming from. So IHI developed a feedstock oil for the HEFA process, and from microalgae, or microalgae, in a British way of saying, pronouncing. It had gone through the rigorous ASTM qualification process and has been approved as a ASTM D7566 Annex A7 in 2020. So it is a commercially deployable technology. So today, ASTM approves total of 8 different technological pathways for SAF, and lucky number 7 is in fact IHI's. We had done the commercial flight in 2021, thanks to ANA and Japan Airlines. And we're continuing on this commercialization effort of this technology. But that's about all I can touch on today. Again, today's topic, or our focus, is on power to liquid. We're now focusing on 2 technologies, and I think many of you would be interested to know about the power to liquid more of a mysterious technology still in the community. So before moving into our technology itself, let me touch on what the power to liquid is, more of a tutorial, more a crash course. So I think the audience today understands what power to liquid, or PTL in short, but what it is, but just a brief introduction. It is a SAF production process from the hydrogen and carbon dioxide, like pictured here. Since this collection of these raw materials, hydrogen or CO2, especially from this renewable source, it would require, say, vast amount of electricity. So that's where the this moniker PTL, or conversion of electricity into liquid fuels, is coming from. I think many of you know that. And the conversion technology itself isn't really a magic. It's based on catalysis, which is one of the competency of IHI and A-Star. And it's a very, very low in TRL still. And as of 2025 or a range of 2030s, as compared to the bio-based SAF, like such as HEFA or ATJ, but it's mainly due from the the electricity cost or hydrogen, green hydrogen cost, and we're emphasizing that we can see a lot of future in this technology. So more of a commercial background, I guess. So I think the audience today is aware of this and have seen these charts in countless times. But we have an imminent need for sustainable aviation fuel to decarbonize the fast-growing aviation sector, particularly our home, Asia, will be the key driver to the aviation travel growth. And the right chart shows the SAF technology mix outlook up to 2050. And you're all aware of this. Whether you believe in this or not is a different story or a different discussion. But the common understanding of this industry is that the tangible, say, bio-based SAF, such as alcohol to jet or gasification, Fischer-Tropsch or HEFA, have a certain availability limitation. And whereas PTL, since it utilizes, let's say, intangible gaseous limitless material, like the chart here, prepared by ICAO, the PTL, this is part in blue, will take over the, let's say, majority of the supply of SAF technology mix. And yes, I do know that water or CO2 or green electricity is not limitless. And the idea here is that you can see the background of where the PTO is talked about. I think you're all aware of it. So just don't immediately jump over and burn me, okay? So we talked about the outlook of what the demand will be. So let's talk about the outlook of what the technology will be. So for PTL, there are more than the processes or technologies shown here, but generally there are 3 technology routes available or will be available today. First one, well, this one shows it from left to right will be the the production process scheme. First one is Fischer-Tropsch. I think many of you are very, very well aware of. And first one is commercial deployable. The second one in middle is commercialization in progress. And the third one is the IHI or the IHI A-Star or our method. So first one is the Fischer-Tropsch process. It's widely really recognized as a technology route for the waste to fuel production. The raw material for the Fischer-Tropsch reactor is, as seen here, the carbon monoxide and hydrogen, or syngas in short. And syngas can be produced from the reverse water gas shift, where the biomass syngas can be produced from the gasifiers. In any case, this is the most orthodox approach for the CO2 conversion to SAF or power to liquid. The process itself is ASTM approved. I do know there are a few cases already in the world, be it the demonstration plant or semi-commercial scale plant that is running in this process, this technology. Second one is methanol to jet. It's a work in progress, but the very realistic work in progress. I think the audience knows today that alcohol can be converted into jet fuel through alcohol to jet or ATJ process. And however, the only approved ATJ technologies are that either from the ethanol endorsed by LaLanzajet, who is a newly joined member of ASAFA, and isobutanol, which is endorsed by GEVO in the US. And methanol is also an alcohol, very, very common alcohol, but it's not really within the scope of ASTM certification yet. Although the process itself is very robust, and I think we can see this approval of methanol in maybe coming year or 2 years, which is very, very fast or very, very early in the ASTM approval context. And methanol can be acquired from the CO2, either from the syngas route or just direct conversion CO2 technology is available. This is a commercially available methanol synthesis process. So it's more of an integration of commercialized processes. Just that for the wording or the concept of the integrated concept itself isn't approved in the ASTM yet. And some of, I think, the fuel producers are actually not in Asia, but the planning on deployment of this methanol to jet process. So the third one, modified Fischer-Tropsch process, is the IHI historic method, is more of an integration or a combination of these two processes. So our modified Fischer-Tropsch reactor will, well, again, I'm not a strictly technology person, so I think Lu Wei can explain it better. But it's a direct conversion of CO2, not a syngas, direct conversion through the single reactor into the olefins, which is the intermediate, sort of resembles the intermediate of the alcohol to jet process. And so in that sense, theoretically, it can be integrated with the commercially available catalysis to produce sustainable aviation fuel. And where we are today is that we came to produce very high yield olefins from this modified Fischer-Tropsch process. And we're currently working with various partners to seek for the upgrading technology. So that's where we are at. So that was a general overview of the power to liquid. And let's go to the IHI's technology, which I'll probably will skip over in many ways for to become a segue for the Lu Wei. So we have been working on this technology again with the A-star or easy squared for A-star easy squared for roughly maybe 4 or 5 years now. And in 2022, we had made a news release that we were succeeded in obtaining high yield of olefins. Again, it's the intermediate of the ATJ process from the catalysis from the CO2. Again, one disclaimer here is this is R&D. This is from the lab. So it is not a green hydrogen. It is not a green CO2. But you know, CI values, you cannot ask for the CI values, but this is more for the technology, let's say, showcasing. So 26% yield, this is a C yield of olefin achieved, which is, it says the world's top level, you know, this is a, publicity purpose. But in the lab level, with the direct conversion of CO2, we were able to attain very high yield of olefins. And so currently in Singapore, in the Jurong Island, I can touch on this later on, but the development work is going on this direct FD process. Direct FD isn't a, let's say, trademarked expression of IHI nor A-star. It is more of a nickname for direct conversion of CO2 into the hydrocarbons. Anyway, so in Singapore, we're working on the more higher yield or conversion of CO2 into the hydrocarbons. And at the same time, we're working with the technical development on the jet conversion. So notionally, I think we can get we can just integrate the commercially deployable upgraders, such as maybe like oligomerization. This is not a definitive. We're just trying out various catalysts at this point. Maybe oligomerization, hydroprocessing separation, and we can likely with this that we can acquire the SAF made from this power to liquid concept, maybe within a year or so. And this concept itself needs an ASTM, new ASTM approval. So likelihood, I'm not sure if it is going to be revision of the current annex, current Fischer-Tropsch annex, or new annex, but the likelihood from my personal experience would be the new ASTM annex. I think Lu can elaborate more on this one. So I'm going to just fast forward this, but the IHI cannot single-handedly develop this. IHI do have an experience in catalysis, but this is truly a work of the partnership with A-Star EZ² on this development of the CO2 modified Fischer-Tropsch process. So the lab development is still ongoing. We're working on improvement, but at the same time, very important piece is that the battle is not happening in the lab, it's happening in the field. So we're going to scale up. We're going to work on the scale up of this technology, which is this. I know that many of the audience here, I would like to thank you for coming over to see this facility last month in January 15th. We have built POC demo facility in Singapore in the A-Star campus in Jurong Island. It began operation this year. Output, again, it's really small. It's 5 kg of C5 plus hydrocarbons per day. But still, it's a one huge giant step away from the lab scale. And I think it has a lot of meaning to it. So it is currently commissioned and up and running in Jurong Island. And again, we had PTL SAF opening ceremony in January 15th. I'd like to thank you to the colleagues who took time to come over to the Jurong Island. And thank you, Asafa, also for coming over. Here's a picture of 3 of you in front of the facility. So that's about all from the introductory, say, presentation from IHI. But so let's throw some wrench in. I think this platform is more valuable to have more just introduction of or a commercial being the advertisement of a company. I think it can be more than that. So what can we make of PTL in Asia? What's the meaning of PTL in Asia? And I think everyone agrees that there is a huge obstacle, especially in Asia, the electricity, the green electricity. So the energy outlook of the world is, there's many ways of seeing and many data there. And you can argue, we can argue all night. But I think, especially in the APAC region, we can all agree that the renewable energy isn't going to be handy in the future to come, or let's say at least in the 2040s range. But there's many scenarios out there, and current situation in the APAC region is this: the fossil is, let's say, 70%. I still think this is pretty high for than what I thought. But in 2040s range, in business as usual, we could probably see maybe like 60%. So majority, say, power coming from the fossil. And maybe if we can do better, then you can go to maybe 80%, nearly 80% of renewable energy. If we could deploy or could do all the magic to endorse or introduce alternative energy. But still, even for this aspirational, let's say, aspirational outlook for in 2040s, the fossil will be around. Fossil-based power generation is still around in 2040s. So would there be a room for PTL? And well, easy answer will be no, and easy answer will be very pessimistic. Even for Japan, the situation is very, very difficult. But still, would that mean that so we can just deploy? Is PTL a thing for Europe or America? One thing is that this is the feedstock potential. This is the bio-based feedstock potential for the ASEAN regions, not strictly on Asia, but the ASEAN regions. everyone knows this, report. It's a fabulous report by RSB, sponsored by Boeing. And the easy answer is that, yes, we do have ample bio-based, say, feedstock in the ASEAN region or Asia, maybe. But still, if we look at this, well, HEFA is, undoubtedly very robust. And alcohol to jet may be really robust technology as well. But gasification plus, Fischer-Tropsch process. I do know that there is some cases in already a project going on in Philippines, and Fischer-Tropsch process tech projects are ongoing. Maybe people are considering this, but still, gasification plus Fischer-Tropsch has a lot to prove. And I do hope for all the success. But can we just rely on this, let's say, numbers or outlook and say, well, we don't need power to liquid? I think there's a value in at least making a small scale approach maybe, to deploy power to liquid within the Asia region, just in case that some of the scenarios could face some adversity. Maybe power to liquid could, let's say, supplement the future SAF demand in the Asian region. The IHI is more safe idea for a notional roadmap for the commercialization of our technology. So we are currently here in a Jurong Island. We started with a bench scale plant, or a very small scale plant. We're emphasizing the demonstration scale in coming years, in very near future. A lot of paperwork or the calculation work is going on. A lot of conversation going on with the potential partners, and we would obviously welcome anyone who would be interested to have a conversation with us. And our notional target is that by 2030s, we go into commercial, or in a sense, acquiring the ASTM approval by 2030. And we have done that in the microalgae SAF, and I think we can conceivably say that by 2030s, we'll be able to attain that. So I think that's the end of my presentation. I hope I haven't gone over time.
You haven't.
Okay, so back to you.
Yasu. Yeah,
Okay.
you haven't. Thank you very much. And again, I mean, we were at the launch event of the joint test rig in Jurong Island on January 15, and we were very impressed by the association of IHI and STAR, and I think that's what gave us also the idea of that webinar. And we were delighted to see that, okay, we have R&D on eSAF in the region, because we know that so far, I mean, the whole low-hanging fruit is HEFA for the region, especially with the feedstock in Southeast Asia. But we need to look at the alternative, and we need to look into all directions. And I think that's congratulations to you and to Luwei for going that direction. Yasu, we have some questions for you, and I think we have a bit of time to take them.
Okay.
Do you see the questions, or do you want me to get into?
Yeah, let me. Oh, it's on the chat, or?
Yeah, it's on the Q&A.
Okay.
One thing, while you look at the question, one thing for you mentioned the study from RSB in partnership with Boeing. And it is an interesting study. It's only focusing on ASEAN, and I think, yeah, it was mentioned. I mean, here, of course, we already saw the needs for gasification and Fischer-Tropsch and P2L, right? But if you look at Northeast Asia, and I'm thinking about Korea, I'm thinking about Japan, for example, and the alcohol to jet and the HEFA feedstock in particular are going to be smaller as well. So definitely, to ensure self-sufficiency in terms of SAF for Asia region as a whole, we need that P2L. And again, in the Middle East, there is no question as well. I mean, they need P2L as well. So I think there is definitely a case, a very strong business case on the P2L.
Yes, I agree completely. And the enigma there is that we don't have a bio-based feedstock, especially like here in Japan, but we don't have a renewable energy. We lack renewable energy as well. So yeah, okay, but I agree with you. sorry for my low IT skills. I couldn't not really locate the chat. So could you maybe like
okay, yeah, sure.
out loud?
Yeah. So we have a question from Lupita. Okay, we don't have your surname, Lupita, but
okay.
quite well. So what is the efficiency of this demo facility? How much SAF can be produced, and what is its byproducts?
Very good question. Hi, Lupita. Good to see you again. Yeah, it's the yield is 100 kg CO2, and we get 5 kg of the hydrocarbons. And byproducts, we're looking into this, but the notionally, I think we can get some diesel and naphtha. That would be the very, let's say, very common byproducts for the ATJ or HEFA process. But yeah, so to simply answer your question, yeah, those will be the byproducts.
Okay. So next question is from Gogim Song. What are the advantages of P2L over the other A2J and HEFA processes? And what are the economic conditions needed for it to become economically competitive to the others established technology?
That's a very, very good question. For me, you were laughing. Yeah. So one of the advantage is, like I mentioned, the feedstock is not a physical product. It's a gaseous product, and theoretically, we can have, let's say, limitless supply of feedstock, especially CO2. Of course, for like direct air capture process, CO2 in the atmosphere is like 400 ppm. So how much energy would be needed to produce or capture CO2 would be another question. Not a question, but definite advantage is that the simplicity of the feedstock. It's a gaseous. It's a very let's say, because of the gas, it's a more like a mono process. You don't need a segregation. Well, you do need a segregation, but you don't need a physical segregation as much as, let's say, Fischer-Tropsch or HEFA feedstocks. And the condition is obviously electricity. Condition to realize this is electricity. And yes, and to make it sustainable, it has to be green electricity. So we will need a lot of green electricity capacity to be able to produce a cheap green electricity, thus cheap green PTL SAF.
Yeah, I tend to agree with you, but all right. Cool. Thanks you, Yasu. No, it's not an easy one, but at the same time, if we don't look into it with our R&D, then there's no way we're going to make it financially viable anyway.
Yeah, exactly. Yeah.
We had a question from Mads. So Mads, okay, first, thanks for your positive comments. Really interesting perspective and presentation. Thank you. So the question is, how do you tally these SAF ambitions, including P2L, with the lack of hard mandates across a lot of APAC in the near term, at least? Before producers can start looking at such projects, airlines need to engage in some form, and they are reluctant where there is no hard mandate. No, I'm not sure the question is for you, Yasu, but if you need my help, I can jump in that discussion if you want.
Oh yes. Yeah. Okay. Yeah. Well, first of all, well, thank you very much for the comment. And yes, I cannot answer that question as of right now. And but we do need a coalition effort. And in order to have such a framework, like mandates that could boost the development of power to liquid, again, it kind of like goes back to the things that I mentioned initially, that this coalition effort to be able to address this. And I'm really grateful for ASAFA to be able to provide opportunity like this. And we would like to continue being engaged with the audience or the community to accelerate the development and mandate, hopefully, of PTL.
Yeah, Mads, if you allow me, Yasu, I'm gonna give 2 minutes to talk to that, and Mads happy to, and it's not for Mads only, but everybody. I mean, don't hesitate to come back to us if you have further questions for the speakers today, but also for the association. But that's exactly why the association has been created, Mads. And in fact, we want to gather, and you know that airlines have have certain opinion, producers have another one, financiers another one, etc. So everybody has a different opinion and a different targets. But ultimately we are all on the same boat. So the association is trying to gather all that ecosystem so that we can come with a consensus all together, and then go and talk to governments and put in place whatever policy makes sense. So will it be mandates, targets, but we need also, we cannot ask airlines to pay for the full price of for the full premium of SAF, you know, without having any financial support on the other side. And that's why airlines are against mandates, for example. And I discussed with a lot of airlines in Asia Pacific, and I can tell you they have a very strong position on that one. And in the field, and in Middle East here as well, and they have the same position. But again, we need to come with not only a mandate, but we need to come with the global approach. And I think that would include what it needs to include, but that will include incentive for the purchase, price reduction with maybe book and claim, with maybe CDRs, with different options. But definitely that's something we need to look into it, and we need to look into it as one, not as every single organizations or industry pushing for their own solution, because we're gonna go nowhere. Okay, we have more questions rising. I think we have 5 more minutes for the questions, and then we will move to our next speaker. Is that okay with you, Lu Wei, for this one? It's 5 minutes. You're gonna take the floor.
Sure. Yeah.
Okay, cool. So next question, Yasu, is from Michael. How can eSAF be relevant to Asia when any renewable power will be needed first for decarbonization of their power grids and for virtuous industries like steel and fertilizers? When might there ever be a renewable power surplus? All right, I think you tackled part of it already within the previous question.
Yeah, it's obviously a very difficult question. Again, and very good question, or very good point, that obviously we're going to lack renewable energy, and currently we do lack and this is not an issue only in aviation industry, more of a global industrial enigma, or the conundrum that we have to really solve. And yeah, so in that sense, do we see, or do I see major deployment of PTL in Asia? That's, at this point, I cannot see that. But like I said, I mentioned in the WT, or waste to energy plant, we might be able to deploy like more of a localized grid, closed loop, very small scale maybe. But there are regions where like in Kagoshima in Japan, that we're having the too much solar is produced, and they're shutting down the production of solar during the daytime. Again, I'm not talking about anything definitive, but I think if we look very very, very close, have a microscopic view of each region, maybe we can find some,
agree.
I agree. Some green energy. So yeah.
Michael, if we take the United Nations definition of Asia, it's 48 countries, and it's include also countries from the Middle East, for instance. And if you look at on those countries, like you have some potential. I mean, Yasu, you just mentioned in Japan, you have Sarawak also in Indonesia, in China also, Vietnam, they're investing in green energy. You have, of course, the Middle East, which is a big player. India is also looking at it. So again, first thing, there will be, I mean, it's improving, and there will be more renewable energy accessible in Asia. Will it be enough for P2L? I mean, story will tell, right? I mean, but we're here. And the second thing as well is, don't forget that, I mean, we are promoting a SAFA regional approach, but ultimately we need an international and a global approach, meaning that the technology that is developed today by Yasu and Lu Wei on the eSAF that could be duplicated or replicated in other region if need be, because if it's, I mean, we believe it's going to be efficient, and where for regions where the renewable energy will be more abundant, for example. Not mentioning, of course, about the waste to energy and other solutions that will create also energy, right? So again, we're not there yet, but that's work in progress, and we need that technology assessment, that new ideas to bring additional feedstock, because we know we're going to be limited anyway with HEFA and A2J ultimately, right? So
yeah. Mm-hmm.
All right. We have 1 more minute, so maybe one last question. And for the other questions, guys, ladies and gentlemen, don't hesitate to forward them to me, and we will liaise with Yasu and try to come back to you with great pleasure. So last question. All right. So, okay. One coming from Sam. For the current plant, what is the limiting factor for producing more than 5 kilograms per day on hydrocarbon? Is it the CO2 capture process?
That's kind of like a yes and no. The capacity for this Jurong Island plant, I think maybe Lu Wei can speak a lot better than me, but the one thing is the supply. And again, the feedstocks, hydrogen and CO2, they are not green feedstocks, or let's say they are not necessarily a green feedstocks. More we're doing this for technological demonstration or technological improvement, and green factor is more of a separate issue. So there is some certain limitation, I believe, as far as I understand, to the A-Star campus, and the maximum, or let's say the minimum scale that we could deploy and see the let's say scale up to observe the scale up process was the 5 kg output of the hydrocarbons. Maybe like Lu Wei can state more beautifully than me, but yeah, that's my opinion.
Yes. So I think it's a good transition. It's a good transition.
Nice segue.
Thank you. Yeah, yes, as you can see, this 100 kg of carbon dioxide per day is already about 50 to 100 times scaling up from our lab research. So I think we can't like scaling up up to 1,000 times from that scale. So we need to at this scale to collect more engineering data, more realistic data, which will allow us to further improve our catalyst design as well as engineering process design for the future further scaling up plant. I hope that answers your question.
Thank you, Lu Wei. So now it's going to be time to introduce you to the audience. Thanks, Yasu, for this very precise and interesting presentation, and good way to introduce more in-depth discussion with Lu Wei. So Dr. Lu Wei Chen, you are the Division Director for Carbon Future Energy Carriers and the Senior Principal Scientist at the Institute of Sustainability for Chemical Energy and Environment, or from A-Star. Okay, we call it Ice Cube, if you don't mind. That's going to be easier for everybody, right?
Easy square.
I square, sorry.
Easy square.
Easy square. Thank you so much.
Yeah.
So you had got your PhD in 2000 from the Department of Physics, National University of Singapore in US. You're currently leading the Division of Carbon Conversion and Future Energy Carriers. You're also an adjunct associate professor at the Department of Material Science and Engineering at the NUS. Your research interests include the development of catalyst materials for carbon dioxide capture and utilization, renewable alternative energy, and biomass valorization. Yeah, what's interesting also is that you're both active in both academia and industrial related R&D, because you published a lot of papers, more than 90, if I'm not mistaken, with more than 6,500 citations and H index for 42. So some of your papers have been highlighted in prestigious catalyst journals and as research highlights of newspaper and A-Star websites. So you started to work with several famous engineers and chemical industries such as ABB Lummus, Rolls-Royce, Degussa, Lanxess, and IHI since 2000. So 8 patents have been awarded, and 2 of them have been commercialized. In particular, you led also the catalyst development of CO2/CO2 methanation projects in collaboration with IHI to the demonstration stage. So Lu-Wei, please, the floor is yours.
Okay. Thank you so much for the kind introduction. It's a very long introduction.
Yeah, but it's deserved as well, right? I mean, yeah.
Thank you very much. Am I sharing the full screen of my
Yes.
presentation?
Perfect. You are.
Okay. So thank you so much for the kind introduction. And today I'm very grateful to have this opportunity to share some of our research work together with IHI in the CO2 conversion to SAF. And I also would like to take these opportunities to give you a brief introduction of A*STAR, our institute, and our research capability in catalysis, and hope we can find opportunities in future work together for the sustainability. So first of all, A*STAR means the Agency for Science, Technology, and Research. So for those audience, if you're not in Singapore, maybe not so familiar with A*STAR. So A*STAR is a government lead agency for dedicated research in 2 main areas. So one is science engineering research area. We have chemical materials, energies, electronics, infocoms, robotics, automation, etc. And we have another big area is biomedical research, including biomanufacturing, food, medical technology, pharmaceuticals. So our institute is called, let me show my pointer. So our institute is called Institute of Sustainability for Chemical, Energy, and Environment. So in short, is we call it as EZ squared. And our institute is located at Jurong Island. It's out of the mainland of Singapore. And Jurong Island is a chemical hub for Singapore. And of course, the industry is based on petroleum base as a feedstock and also energy source. So within the island, there are more than 100 multinational companies, third-party utilities, and waste pretreatment, storage, and etc. So because it's very carbon-intensive base industry, so only Jurong Island alone, it contributes to more than half of Singapore's total carbon emissions. So although this carbon emission is only counted, Singapore's carbon dioxide emission only counted 0.5% of the global CO2 emission, but we also have a very ambitious target, which will determine to achieve net zero emission by 2050 as part of our long-term low emission development strategies. So to green the Jurong Island, we have to shift away from fossil-based industry into more renewable resources, such as alternative raw materials. We should shift to biomass, carbon dioxide waste material, and we also need to use a new energy mix, such as clean energy carriers, ammonia, green electricity, hydrogen, etc. So with this kind of shift of the feedstock and energy mix, we hope we can significantly reduce the carbon emission and green this Jurong Island. So our institute will, as we allocated at this chemical industry hub, we're here to support the chemical and engineering and energy transition. So our strategy is to develop a portfolio IPs and also a platform and infrastructure as a critical enablers to accelerate the innovation and bridging the gap between lab research and industrial application. So our institute currently is about 250 staff, and with about 45% of a PhD holder as researchers and other research engineers, and also corporate support. And we are also a very multinational research organization, and we have staff from many different countries all over the world. And there are four main research directions. So one is the carbon conversion future energy carriers. We mainly look at CCU research and also new energy carriers. And we also have a chemical biotechnology, synthetic bio, and resource circularity to get circular materials such as polymers, biodegradable polymers, as an example. And we also have a division focusing on develop emerging technologies, prepare for our future sustainable development. And under this, we also have a very two important critical enablers. One is digitalization and automation. So this will help us to speed up our innovation. And we also have a division focused on process engineering and safety. And this will also accelerate the deployment at scale. And here are a few examples on some key activities for CO2 emission. So for example, our institute work on CO2 capture and mineralization. So these are two examples showing our activities. Mainly, we are using capture the CO2 into a solid form, for example, into minerals as a carbonate. And these alternative, these carbonate products, after this carbon dioxide fixation, it can be used as an alternative sense, for example, for land fuel or other applications. And we also have many activities on chemical conversion of carbon dioxide to fuels and chemicals, such as methane, like olefins, methanol, higher alcohols, and jet fuel. And we also developing a low carbon, let me, make sure I go back to this slide. Let me share again.
Yeah, no worries. Wait, we are with you.
It's time block my view. Okay. Yes. So we also have a low carbon technology translational test bed. We call it LCTQ. And this is a test bed. The facility is already under a detailed engineering design phase, and we hope it can be ready in a couple of years. And this test bed will mainly focusing on translation our lab low TRL technology into high TRL. So it will be focusing on the technology between 6 to 8. Okay, so now I will switch to our topic on CO2 to SAF. And this work is a collaboration with IHI, as Yasushi-san just mentioned just now. And as we can see here, aviation industry also have a strong need to decarbonize this session. And there are also some mandates being announced. So for example, in Singapore, we require about 1% SAF blending in 2026 for all flights departing Singapore. And by 2030, the target blending of SAF is about 3 to 5%. And from here, you can see the SAF production capacity and the demand in Singapore. There actually is a gap. You can see here, many countries actually currently they have no or very low capacity in SAF production. However, the demand is higher. So there is a gap between the demand and the production capacity. So the production of SAF, you can have different types of technology, as Yasushi-san just introduced. So here currently there are 7 approved ASTM approved pathway. So you can see here like HEFA and other technologies introduced like alcohol, A to J, methanol to J, jet, A to M to jet, and also a syngas Fischer-Tropsch reaction pathway, as well as capture CO2, and also can be a feedstock for the syngas production and to produce SAF via conventional Fischer-Tropsch pathways. And it's not working. Okay, so as you can see here, compared to the you may think we have new technologies which can provide battery technology or green hydrogen as an energy feedstock. However, for aviation fuels, the long, or especially for the long-haul flight, due to the very low energy density of the hydrogen and battery, so the conventional liquid fuel still the main choice for the long-haul flight, even in far futures. So research show use this sustainable aviation fuel is expected to contribute to the 65% carbon emission reduction for the aviation industry. And currently, the main source of SAF is bio-based, so like HEFA. However, you can see the capacity is very limited. So by last year, there's only 0.2% of the SAF counted for the total global demand of the aviation fuels. So as we can see here, bio-based SAF, they will be limited by the availability of feedstock. So some analysis foresee CO2-based SAF can be significantly increase in future and can be another source of SAF production. So as we can see here, utilize of carbon dioxide as a feedstock for SAF can be alternative solution for CO2 emission instead of geological storage. And we can actually try to make value from the waste carbon dioxide. And as we mentioned previously, Fischer-Tropsch synthesis is an important process to produce clean fuels from non-petroleum source, from CO plus hydrogen as a feedstock. So this reaction was discovered for 100 years ago by two German scientists. And currently, there are two major players in the world use this Fischer-Tropsch synthesis technology. They are Yasu and Shell. So as you can see here, the conventional feedstock is CO plus hydrogen. And what we are going to work here is a direct conversion of carbon dioxide plus hydrogen into hydrocarbons. So we call it as a modified Fischer-Tropsch synthesis. So compared to this two-step reaction, well, you need to activate reduce carbon dioxide into carbon monoxide via highly strongly endothermic reaction, reverse water gas reaction. And on the second step, actually, the Fischer-Tropsch synthesis is a strong exothermic reaction, which will further activate, reduce carbon monoxide hydrogenation into hydrocarbons. So what we are doing together with IHI is we will combine two reactions in one reactors. So the catalyst is bifunctional, which allow us two tandem reaction can be happened in one reactor. And so by doing so, we foresee this one-step direct reaction will have smaller carbon footprint, reduce capital costs, and enhance energy efficiency. And so, of course, we need a new generation catalyst to overcome these technical challenges for carbon dioxide. Because carbon dioxide is very inert, and so compared to carbon monoxide Fischer-Tropsch synthesis, this reaction will end up with a lower conversion and lower selectivity for long-chain hydrocarbons. And we definitely also have methane and light olefins, light hydrocarbons as byproducts. So we need intense research to develop a new catalyst. So conventional syngas Fischer-Tropsch synthesis mainly use cobalt catalyst. So however, a cobalt catalyst, it doesn't work under carbon dioxide condition. It will mainly just act as a methanation catalyst. So if you use conventional cobalt catalyst, it will end up methane as the main product. So iron-based catalyst currently is still the best catalyst for this modified Fischer-Tropsch reaction because iron can act as a reverse water gas sheet catalyst, and it also can act for a Fischer-Tropsch synthesis catalyst. And however, the active phase of a catalyst actually is very complicated. So if the catalyst under actual reaction condition, it will have iron oxide iron carbides, and iron carbide also with different structure and phases. So how to control the active size and balance the reverse water gas sheet activity and the Fischer-Tropsch synthesis activities are all the challenges for our catalyst development scientists. So for this catalyst development, we are fortunate to have a platform we call Accelerated Catalyst Develop Platform. And this platform is built in A-Star with several RIs. We integrate with different expertise on modeling, machine learning, and high throughput experimental on synthesis, catalyst screening, and advanced characterization. So we combine with the feedback of these data from experiment and machine learning, we are able to accelerate the development. So within a year, actually, we increase the C5 plus liquid hydrocarbon years by 50%. So this is a very powerful platform for us to tackle the challenges of catalyst development. So as you can see here, we have went through a different stage of catalyst development. And also, in addition to the catalyst development, IHI also work on the reactor and process design. So as you can see here, the initial lab scale reactor, we actually have 3 reactors in series. So by doing so, it will help us to enhance the conversion and the overall yield of the liquid product further. So this is a lab scale at about 2 kg of carbon dioxide feed rate per day, and with the catalyst in the powder form. And this is the catalyst in pellet form, and we have tested as further scale up in the lab as a single reactor tube. And this is the 100 kg carbon dioxide per day test rate, which we just launched last month. So this will allow us to further collect engineering data and also other relevant data at more realistic industry relevant scales. Yeah, so as you can see, we actually have very strong collaboration with IHI in the conversion of CO2 to X technology. And this, our CO2 to SAF project actually was awarded by Singapore IES Institute of Engineering, Singapore, for this CO2 to SAF project. So I would also like to take our opportunity to introduce a bit on our research capability. So as you can see here, actually a catalysis will play a very important role in the modern energy and chemical industry. So as with different times, we are facing different challenges, and different types of catalysts has been developed to tackle the challenges. So for example, in the early 19th, this is mainly petroleum-based chemical industry, and we have silica, zeolite, this kind of transition metal as the main catalyst. And in the 1990s, when there is an oil, 1970s, when there is an oil crisis, and people start to look at other alternatives, mainly still petroleum-based, for example, coal, natural gas, oil sands. And after that, when we have a global warming and we look at more carbon neutral technologies, and for example, now we are all more focusing the research on these CO2-based and biomass-based and waste materials. So we believe catalysis will stay still a very essential role, have us shifting from a petroleum-based chemical industry into a more sustainable and renewable society. So however, although catalysis is very important, but the journey of a technology and catalyst development is very long. We have ideation, synthesis, screening, understanding, and optimize the catalyst recipe in lab scale. And we need to go through a different stage of scaling up before this technology can be really deployed. So usually this may take about 10 years, and the catalyst development is really a bottleneck for this technology. So as I mentioned just now, we have this accelerated catalyst development platform developed in A*STAR. So this platform, we work with Institute of High Performance Computing on modeling, and we also work on machine learning and high throughput experiment automation. So this will allow us to speed up the catalyst development. So the high throughput facility is housing in our institute. So we have this high throughput catalyst synthesis workstation. This allows us to perform impregnation, co-precipitation, so gel, several types of synthesis techniques. And we also have this HTE high throughput catalyst screening system. And this have 16 parallel reactors, and it can be either plug flow form or trickle back modes. And the reactor can be operated up to 700 degrees C. And also, if we want to run at higher temperature pressure, it can be up to 200 bar. Of course, this has to be run at relatively lower pressure. So this kind of platform is allow us to accelerate the discovery or development, optimize the catalyst by 5 times. And addition to the catalyst development platform in lab scale, and we also developing this low carbon technology translational test bed we call LCTQ. And this facility will equip with module reactors, and so it can be plug and play, and also with auto control system, and also a digital twin, and also use cyber-physical integration modular approach for the chemical process technology translation. So the facility is currently under a detailed engineering phase. So with these two, we hope we are able to speed up the catalyst and technology development for a chemical industry. So in short, we work from the technology development from atomic to system level. We do fundamental research to understand the catalyst structure, correlate to the design, to the performance, and we also have a modeling simulation. So this research catalyst design after this research catalyst design, we can have the further development, went through the high throughput synthesis and optimization in this high throughput system and machine learning optimization. And further down, we have a scale up facility and capability. And this will allow us to translate the research catalyst from lab into a technical catalyst, and we can validate the technology at more industry relevant scales. And this will also allow us to have more realistic pilot process and reactor design for further scaling up the technology. And last but not least, life cycle assessment and techno economy assessment is also very important to ensure we're working on sustainable technology. Yeah, I think this is the end of my talk. Yeah, and I'm happy to take your questions if there's any questions.
Thank you, Louis. Very, very nice, very interesting. All right, so we have a question for Michael, but it might have been from the previous one, but it might be still relevant to you, Louis. So
okay.
Do you see the question, or do you want me to mention it?
Oh, I can see it. Okay. More about the modified Fischer-Tropsch product. I see the usual heavy. No, it because carbon dioxide is quite inert compared to carbon monoxide. That's why the modified Fischer-Tropsch synthesis reaction has to be run at a relatively higher temperature compared to conventional Fischer-Tropsch synthesis on cobalt catalyst. That's why the heavy wax product is less compared to the syngas Fischer-Tropsch synthesis reaction. So we also have light olefins, so which will allow us to do downstream further upgrading, such as oligomerization. Yeah, and this reaction as research, as mentioned by Yasushi-san, just now we're starting this downstream process research.
All right, thank you very much, Louis. Any other questions from the audience? Okay, well, in the meantime, thank you again for the two of you. Very interesting, and again, it shows also that we have some potential in the region in terms of R&D and in terms of exploring new technologies for SAF, and I think that's very important. And we as ASAFA, we believe in this because HEFA is just the beginning of the path to sustainable aviation. So yeah, great thing. Thanks again for inviting us. Thanks again for joining today. Happy to liaise anybody between you. Might have another question. Sorry, I'm speaking too fast. Okay, so which collaboration opportunities do you see with European Swiss entities to advance sustainability in your work? Oh, well, that's very precise question, right?
Oh, yes, I think with IHI, we work mainly CO2 to hydrocarbons, such as methane, diolefin, aviation fuels. So we also work on other areas such as CO2 to methanol, CO2 to higher alcohols, and we also have research on green energy and carbon dioxide capture. So I think those areas are the potential opportunities we can work together with others. Yeah. Oh, okay. Another questions, the primary challenges. Oh, yes, I think the product selectivity is quite challenging because Fischer-Tropsch synthesis, we know the carbon number can be from 1 up to maybe 100, usually up to 40. So how to enhance the hydrocarbon selectivity in the SAF range is quite challenging.
Okay, thank you. And Sam, I have an answer for you, Sam. I think the answers to you as a SAF end user, how can airlines support this P2L work? I think the first answer is they can join ASAFA, of course. I think that's quite obvious. No, but that's the best platform to connect with everybody, especially with the region, right? And then of course, then we will liaise and engage and we are expecting to work with A-Star and other partners like IHI and so forth on the P2L working group, right? So where we can work on the roadmaps, on looking at solutions, strategy, approaching, and so forth, right? So I think that's a bit obvious, but that's how it is. All right.
Yeah, I would like to second that too. That yeah, please stay engaged and as a community, and yeah, and likewise that we will continue updating with our progress. And again, if you have a chance to visit Tokyo or Singapore, please let us know. And yeah, let's keep in touch.
All right, the last question for the day, and then it will be time for us to stop this session. But of course, we can continue offline, and we'll be happy to liaise with our partners. So as a team benchmarked the FE catalyst against conventional FE Fischer-Tropsch catalyst, what has the results looked like?
What do you mean conventional? Actually, for us, it's challenges to get a industrial iron catalyst to compare. But we did have prepared some benchmark catalysts according to literature recipe, and definitely when we switch from CO to carbon dioxide, there are some significant changes. So for example, some catalysts, it works quite well in our lab, work quite well on CO Fischer-Tropsch, but it works very poor under CO2 conditions. Yeah.
All right, great. Thank you again to the two of you. Thank you to everybody, ladies and gentlemen, to have joined that webinar. You know, stay tuned. We're gonna have another one next month on a different topic, and on the eSAF is just it's not the beginning, but we just a long way to go. But we will be there with our partners and A-Star and IHI being some of them. Yeah, talk to you soon. Wish you a nice end to the day and a nice end to your week, and talk to you soon. Bye bye.
Yeah.
Thank you, Fabrice.
Bye.
Thank you,
Bye.
Don't forget to give us your feedback as well. Okay, take care.
Yeah. Thank you for the feedback.
Thank you.
Thank you.
Bye-bye.
Bye. Bye.